we looked at using probabilistically checkable proofs to prove hardness of approximation results. Okay, in particular, we looked at proving hardness of approximation for max independent set and max 3 set. Okay, it became evident through those connections that improving the query complexity to constant was very important, and so was having logarithmic randomness, because we were constantly considering all random strings, right? That's how we extracted sort of the CSP, or we conducted reductions. So this is something we still need to prove, and that's going to be the goal on next, actually, 3 lectures. But there are things that we have already proved. In particular, we were able to obtain the desired parameters of interest individually. Okay? So a natural approach, which is the one that originally was taken to prove this theorem, is whether one can sort of not start from scratch, but just somehow build upon these results. Okay? We would like to somehow take the constant query complexity for an exponential size PCPs, but only pay for a polynomial size PCP using ideas from this result. The technical tool that will let us do that is called proof composition. At a very high level, it will let us do precisely that. We will have 2 PCPs. One is called the outer PCP. The other one is going to be the inner PCP. And again, at a very high level, we will inherit the size of the outer PCP and the query complexity of the inner PCP. We want to combine them together to obtain a composed PCP that sort of inherits these things. In particular, if we were to assign roles, what should be the outer PCP? Yeah, the second one, right? This is, we want to kind of take the polynomial size PCP to be our outer PCP, okay? And the inner PCP to be the exponential one, okay? Now, what are we proving in proof of composition? Well, we'll see, okay? At high level, what we're going to do is going to recursively invoke our, our ability to prove things correct. Intuitively, you can think about that the verifier will imagine running the outer PCP, but not actually run it. Instead, it will expect a proof that it ran. Okay? But at a high level, maybe if you've seen maybe other phenomena such as code concatenation in coding theory, this is analogous, right? So you can construct codes over large alphabets and good distance with good sort of good size, and you can have codes over small alphabets, still good distance, but of large size. And if you put them together, you can get so-called good code. Okay. So this notion of composition is, I mean, it's not technically connected, but it is analogous in the sense that also there you have an outer code and an inner code. Now, conducting, from a technical perspective, carrying out this plan actually requires a little bit more work in the sense that the outer PCP is going to need to satisfy certain additional properties beyond being just a plain PCP. And the inner PCP will need to satisfy certain additional properties different from the outer ones, beyond just being a PCP. So in the next 2 lectures, we'll see what these extra properties are going to be for the outer and the inner PCP. Okay? So we'll see that we're going to need, we'll see in 2 lectures why we need the outer PCP to be so-called robust, and why we need the inner one to be a so-called proof of proximity. So the plan now is to sort of not question why we are needing certain properties that will become apparent when we do proof of composition. What we will do today, I will tell you how to strengthen the notion of PCP to that of a PCP of proximity. Okay? Next time, I will tell you how to strengthen the notion of PCP to be a robust PCP. Both of these are sort of orthogonal strengthenings, kind of to some extent of independent interest. And then kind of they play well together once we'll see proof of composition, okay? So I won't say basically anything else about proof composition for today, but I hope the plan is clear. Okay, and in the third lecture, we'll see how they come together. Then we'll finally have proved the PCP theorem. So, all right, so today I want to talk about PCPs of proximity. These are abbreviated as PCPPs. These are kind of really awkward acronyms. So before I talk about that definition, I want to first recall the definition of a plain PCP. Okay, just like a normal PCP, because we're going to change it. Okay, so we say a PCP verifier V for a language L is with soundness error S is a probabilistic polynomial time oracle machine where we have the usual properties of completeness and soundness. So for every x in L, there exists pi such the probability that V given oracle access to pi and input to x, it outputs 1 always, and the probability is over the verifier. When x is not in L, for every pi, the probability that pi will accept x is at most s. Okay, at this point, you should be able to kind of produce this definition in your sleep, right? We've been working with it at this point several weeks. Okay, everybody happy with the definition? Okay. Now, the notion of PCPPs kind of explicitly deals with relations. And that's not really the main difference, because we could, even here, talk about a relation if we wanted. It just doesn't really have any effect on the definition. I could say for a relation R, right? And here in the quantification, I just look at the language of R, right? So you will agree with me that I could have just given the definition for relations. It just doesn't have any effect. When I'm actually requiring something, I'm just looking at the projection of the relation to the instances, which is the language, right? Well, this notation it just says a relation is, a set of pairs, right? Project on the first pair. Okay. So the notion of PCPPs specifically applies to relations only. So we must phrase it in terms of relations. And let me just introduce a couple of notations that we're going to use in the definition. Okay. So given an instance x, we're going to denote R of x to be all witnesses for x. Okay, easy notation. Also, given x and w, so now you're giving me both an instance and a witness. Okay, we're going to define the distance of the witness. Notice the witness is just a candidate witness, right? So it's just some string. We're going to define the distance to the set of witnesses to be, the smallest distance to anything inside that set. Okay, so this is going to be the minimum distance over w prime in Rx, delta w prime. Okay? Now so hope that makes sense. You may wonder what happens if x is not an L. This is an empty set, right? So if x has no valid witnesses, then we define this distance to be maximal 1, okay? All right, so far I haven't done anything. I'm just introducing some notation. All right, so here's the notion of a PCP of proximity. So I'm going to put it next to it here so we can compare them. PCPP verifier. So now it's going to be explicitly for a relation R. And we're going to have one extra parameter. It's called proximity parameter. With proximity parameter, usually called delta, and soundness error S is a PPT oracle machine, like before, such that first, for every x and w in the relation, there exists a proof pi, we call it a proof of proximity, such that now the verifier will have oracle access to w as well, okay? And it has to always say yes, okay? Now, so far, you may wonder, look, there's really no difference, because if I had been working with the relation so far, I could have just put whatever witness I wanted inside the proof, right? So this doesn't really tell us anything. So the difference is in the soundness, which is, you can call it about proximity soundness, that says for every x, so it says I'm actually not saying whether x is in a language or not. And for any w where the distance w to the set of valid witnesses is at least the proximity parameter, and for every proximity proof pi tilde, the probability that the verifier, given this specific witness, candidate witness, and the proof pi tilde, the probability that the verifier would put 1 is at most s. Okay, let's see what's happening here. Here we're saying, what is the verifier thinking? Okay, the verifier has oracle access to two oracles. One is an oracle that it's specifically interested in. It says, here's W, it's a candidate witness. And what it wants to decide, is W a valid witness, or is it far from all valid witnesses? Okay, this is kind of the decision between the two, right? In one case it says, yes, it's a valid witness. In the other one it says, it is far from all valid witnesses, okay? And it's not deciding it just by looking at W, it has some help, right? It's this pi tilde, okay? Now, maybe before we kind of get confused too much, let's at least immediately prove a simple lemma that compares these two definitions. So I claim that this definition is stronger than this definition. Okay, so let's check that. Okay, so one way to check that is to so let's get here. So PCPs versus PCPPs. One thing that we can prove rather straightforwardly, so that we can sort of think about the definition, is that the class of languages that have PCPPs with let's say these parameters, I'm saying completeness 1, soundness S, proximity parameter delta, and the usual things here, is contained in a class of languages, or rather we're really talking about relations, where we have basically all the same parameters, okay? And actually this holds true for any delta, okay? For any delta, this is the case. So this is one way to say, technically, that this is a strengthening, right? We're only asking for more, okay? Okay, so let's prove it so that we can actually convince ourselves. So, okay, let V be a PCPP verifier for a relation R in this class. Okay, we need to construct a PCP verifier for that relation in this class. Okay. All right, so consider the PCP verifier. So let's maybe give a name to this one. We'll put subscript PCPP, and here we'll put a subscript PCP so that we kind of don't get lost. Now, VPCP will take an input X, right? Do something with it, and it has access to one proof. Okay? And let's already think about that this proof possibly is or maybe let's call it bar. But maybe it's not the one that it was prescribed. So, what do we do? So we have a PCPP verifier. We want to construct a PCPP verifier with these parameters. What should we do? So, and it's a very simple construction, okay? Yeah.
And just run the PCPP verifier?
Well, kind of, I want to write VPCPP, right? Pi bar X, right? I can't technically do that because the interface of a VPCP verifier, it really expects two oracles, okay? So really, what I want to do is, as a PCP verifier, I am going to enforce, even though I have access to one oracle, I'm going to enforce that this oracle has two parts, okay? And I will show these two parts to the submachine, right? So I will say, look, whatever pi bar is, I will designate the first so many locations, and those locations I will interpret them as W, right? And whatever remaining locations I will interpret them as pi, okay? And then I run this guy, okay? So that the queries that go here and there, they get translated to different locations in here, okay? Now this is exactly what we're going to do, and now we need to kind of check why this is okay. Okay? Now, for completeness, that's easy, right? Sort of what we want to do is we want to set pi bar to be W pi, where W is just anything in our X, right? We have a condition here that says any W will work, and for any W you can extend it with some extra auxiliary information that will help you, right? So in the completeness case, for a PCP, all we need to do is to find any proof, right? And inside this proof, we're going to stash in the first part a W, because we know later the PCPP verifier is going to want to look at it, okay? And then W is just kind of, the proof, any proof for W, right? And so far, nothing. It sounds like we're just like doing syntactic games. So in Soundness is where actually we see the difference between the two. So why is it the case that the soundness error of the new PCP is actually literally equal to the soundness error of the PCPP? Now here we want to say that fix X not in the relation of R, right? Because that's what it is that we want to prove here, right? Now we're going to say that we also, regardless of whatever proof by tilde we write, which remember, because of the way that we have constructed a PCP verifier, this one will look like some W tilde, right? And stuff, I don't know, let's call it pi bar prime, right? Whatever it continues, right? What do we know? So this is the condition that we have, right? Why do we know that the PCPP verifier is going to accept with at most probability S?
Yeah. Delta is greater than 0, so that in the PCP case, you're considering delta equals 0.
Well, right now, delta is something, right? What is, delta is a lower bounding, a value that is between 0 and 1, right? So delta really sits between 0 and 1, right? Here we are given a delta, let's say 3/4, okay? That's what we have. We know that if the witness is at least 3/4 away from any valid witness, then we're good. But are there valid witnesses? No, right? So what does it mean? It means that regardless of what's written, the distance from X to the set of valid witnesses is 1. So therefore, this kicks in. Okay? So, yeah, I mean, kind of, R of X is empty. Therefore, the distance from W tilde to R of X is 1, which is at least delta, because delta is not going to be more than 1. Okay? So, kind of a VPCPP accepts with probability at most S. Okay? So what is this basically teaching us? Is that the strengthening of this definition is not in the completeness or soundness, but it's in between, right? This is interesting when X is in L and W is actually a little bit away, or I mean sufficiently far away, right? Because kind of when X is in L, when you fix X and W both good, or X is not in L, then kind of we were covered already. We already knew what to do, right? These proofs of proximity are specifically geared to tell you more, okay, that even if X is in L, but W is far from all valid witnesses, you still reject. Okay, this is a new capability that we didn't have before, right? If X was not in L, then we would reject, but if X was in L, there was just one way to accept. We didn't have further discriminants, right? Here we're saying that we have a specific W that we're interested in, and maybe there's plenty of valid witnesses, but this particular one is far from all of them, okay? And then we reject, okay? So it's a new capability. This pi here is called a proof of proximity because if it works, it witnesses that your W cannot be far from a valid witness, okay? So, wait, so that's kind of what's happening here, okay? Are we good? Because now we're about to construct these things, okay? So we should be fine with the definition. Okay? All right, so question is how to construct, so that's the question we're gonna answer today, how to construct PCPs of proximity. Okay? And you know, we were spending weeks collecting tools to construct PCPs. It would be frustrating to have to go back to the beginning and try again with a notion that is only stronger, right? So what we want to try to do is to recycle, okay, to start the things we already know and see if maybe the constructions we have already lend themselves to achieve this stronger property. Because remember, one is a definition, another one is a construction, right? Constructions eventually get wrapped up in definitions, but they may have more than the definition gives you, right? So we're going to try to do that. We're going to look at the specific natural constructions that we have and see how far we are from achieving a stronger definition, okay? So let's kind of, what I'm going to do now is I'm going to try to kind of abstract away what we've done so far for actually either of these. We can actually view the construction in both cases through one approach, okay? And we're going to try to sort of see how we can augment that approach to achieve proximity. So far, we have constructed PCPs as basically something like this. We have a proof, and if I kind of look inside the proof, what I find is allegedly an encoding of some candidate witness W, right? And some auxiliary information that the verifier will use to check that whatever is encoded here is a valid witness, okay? So in terms of examples, for the exponential size PCPs, the proof was a Hadamard encoding of the tensor product of W with itself, and actually the auxiliary information was, there was no auxiliary information. That was kind of, that was all there was. Okay, that's the exponential size PCP that we've seen. And the poly size PCPs that we have seen where basically I take the loading extension of the witness, and then I throw in more proofs, many proofs in fact, for all the possible sum checks. Remember? We had this pi1 and pi2. There were extra things that would let us check satisfiability of W. This was for the satisfying constraints, and this was for the Booleanity checks, right? And each of these on their own was a tree, an unrolled sum check, okay? But both of these conform to this pattern. Okay, but that's just how the proof looks like. In both cases, the verifier had a canonical form. Okay, kind of this, the verifier really had sort of pretty much looked the same at high level. So we had the verifier. It was given access to a candidate encoding, candidate code word C tilde, and some candidate auxiliary information, right? And the first step was, you know what, like even before I think about satisfiability, let me make sure that whatever is written here is close to a code word, okay? So it runs what you can think about as a proximity test to check that C tilde is close to the encoding of something, right? So it checks that C tilde as a code word is close to the encoding of something, but we don't know yet whether that something is of interest to us. And second, it will run kind of a SAT test, satisfiability test. I don't mean SAT language, I mean some satisfiability test to check that W tilde satisfies all the constraints. Okay? And again, to come back to these two examples, we can very precisely say what was happening in the two cases. For exponential size PCPs, can anybody say what was component 1 and component 2? Yeah?
What was load pretest?
For exponential size PCPs?
Oh, sorry, no, linearity test.
Linearity test, yeah. And actually, I would say something else as well. So what's the encoding here? Oh, it doesn't matter too much, it's just how we draw lines. But I would say that the correct analogy is linearity plus tensor. Tensor doesn't care at all about satisfiability, it's just about the specific way that we're encoding information, okay? So this is linearity plus the tensor test, okay? And the other one was just basically taking a random subset sum of all the quadratic equations, right? So it just kind of random, let's call it a random subset test. Okay, so that's kind of the analogy for poly-size PCPs. What was happening? By the way, the random subset test, you can think about, there's also a question of where does self-correction sit, right? I kind of shoved it under the carpet right now, it's not very important. But you can think about it as, the third component here, okay? Or thinking about it as maybe part of 2, right? So that when you are running your SAT test, you're accessing correctly W tilde. In particular, in the exponential size PCP, we also had self-correction, though we didn't have it just out of luck in poly-size PCPs. Anyways, so what was component 1? The loading test, yeah? And nothing else really, because we were just straight up running, encoding via logic extension. And 2 was what? Yeah, whatever had to do with these things, right? So this was the sum check tests. But the point is that, you see, we're just doing the same thing at high level, just kind of relative to different encodings, okay? And then, of course, the choice of encoding then would kind of ripple back and change our arithmetization, but we had somehow in the proof already a witness, okay? Notice that that is special to our constructions. The definition says nothing about a valid proof containing witnesses. It really doesn't, right? All right, so given this sort of general pattern, oh, and then in sum, for these constructions, basically what we proved is that if VPCP given C tilde and aux tilde equals 1 with high probability, say more than a constant, then we know that C tilde encodes, or rather is close to, let's say, distance of C tilde to encode W tilde is, say, small for some W tilde that is valid witness. Right? That's what we did in the soundness analysis. Okay? In both cases. So I claim that at this point there should be like an idea to construct how to construct a PCP of proximity. Any thoughts? Yeah.
We're running a linear test with some proximity or local test with some proximity error, right? So does that sort of translate somehow?
But we already kind of encapsulated it in the statement, right? We're saying that we're running that guy, and because it works, then we know that the alleged encoding is in fact close to an actual encoding of a witness that is valid. Okay? So the fact that we're running a proximity test, I already summarized it in like this implication. But remember that, like, syntactically, what we're trying to achieve is this capability, okay? So I have a witness that is given to me, and then I have a proof that I have no control over. It's also given to me, but I'm interested in that witness, okay? And the proof can contain whatever. So if you're a PCP, if you want to be a PCPP verifier, you get a witness, okay? That's the witness you must say something about. You get also proof. Maybe it's of this form. Let's say it is. It looks like that. What should you do? Sure, you can run this one. You will learn that inside the proof there is some witness, but that may have nothing to do with the witness you have at hand, right? Right? So how do you reconcile this? Yeah.
You run that encoding test on the witness you want to learn things about? Right?
But the witness is not encoded, right? It would be nice if the witness were encoded, right? But it's given to us in plain form, right? And our distance guarantee actually is measured against the raw witness, not its encoding. But it's almost, right? So I have an encoded witness, basically, right? So what should I do? Yeah?
Like you decoded some random points?
Yeah, that would be an idea, right? So if I run my PCP verifier, I know that, and it succeeds with, look, if it fails, then whatever, just reject, right? If it succeeds with high enough probability, I know that inside the proof there is some valid witness. That's great because valid witnesses sit here, right? So if I have a W and I want to catch a W that is far from all those guys, then if I found some way to compare them, say at a random location, then I should be able to reject with probability that is proportional, let's say, to their distance. Okay? So I want to leverage that fact. And of course, we need to kind of potentially decode, or we may have to do other things. But at high level, this is plausible, okay? So let's kind of work out a first attempt that's actually not going to work, and then we're going to fix it, okay? So, so the idea basically means of run the plain PCP verifier, and then also run a consistency test between W and W tilde, where W tilde is whatever is encoded, assuming the PCP verifier is has accepted with high probability. So let's try the first attempt, and the first attempt will actually try to basically even not decode, because the encodings that we have used so far actually have as a subcode word the witness itself. So, for example, note that for the encodings that we used, we have that an encoding of W, or anything really, looks like W and other stuff. Okay, somehow, like when you encode the message is still there, and then you add more stuff, like redundancy. Okay, so let me give you an example, actually, again, with those two things. So when you have the Hadamard encoding of W tensor W, and you look at a location Z, what you will see at the location Z will be the inner product of W tensor W and Z, right? Because the encoding of a vector is the linear function defined by that vector. In this case, the vector is W tensor W, so here it is, right? At the location Z, we'll find that function evaluated at that point, right? So what? Well, I claim that if I look at a very special location that you guys will tell me, I will find Wi. So what should I put here to find Wi here? So there is a particular location that I know that if I look at, I will find Wi. So think of this as a matrix maybe, or an unrolled vector. What should I put here? I should put something of length n squared, right? Which vector? Yeah. That's not a vector. That's a tuple. I should write a vector. So probably it's going to be a delta function, right? That's going to have one entry being 1 and all others being 0. Which entry is going to be? We want to be the I, I entry, right? But really, like, one way to say it is that it's this one. It's EI tensor EI, right? So this is telling us that if I have the encoding of something and I'm interested in that something, all I have to do is to look at some special locations. There's kind of a well-defined embedding, right? So that's true for Hadamard. It's also true for the LDE. If I take an LDE over W, okay, how were we taking loading extensions? Well, we were taking W, which had n locations, right? And then we were just kind of folding it into a hypercube, right? And extending it. So, but when we extended the hypercube is still sitting there, right? So if I just look at the ith point in H to the M, the hypercube, then what you will find is Wi. Okay, I'm not going to write this precisely, but you have to agree on some a canonical embedding of 1 through n into h to the m, okay? And the ith location in W would look kind of mapped to a specific point in here. So if you have a valid log extension, you look at that point, you should find Wi. Okay? All right. So by the way, these encodings are called systematic encodings. Is the terminology that comes from coding theory. A systematic code is one that when you apply to a message, the message is kind of part of the code word and then just other stuff, right? So so far we've just made the observation that the encodings that we've used so far are systematic. Okay, meaning that the witness that we think is there is actually just sitting there. Okay? It's part of the proof. So now we have a candidate PCP P verifier candidate. Okay, let's write it. The PCPP is given W, okay, and then the particular proofs that we'll consider have this form because we're constructing something, so we can choose how it looks. Remember, W is not like adversarial, just like given to us, but then here we don't have any control what's written here. And what are we going to do? Well, first we're going to say just run the PCP verifier on this thing. Just ignore W for a moment. Just run it on the proof, right? So run. Rather check that. The PCP given the proof C tilde aux tilde x equals 1. Okay? If it rejects, we reject. Okay? The second step is we're saying, okay, fine, it passed. Possibly it's because it passes with high probability. So now we know that C tilde, is close to something that looks like that. Okay? Now we also know that we have a systematic encoding, so we know that this code word looks like W tilde and other stuff. And I'm reordering things, but W tilde would be spread out in some way. And now we go back to the suggestion of saying, okay, we have a satisfying W tilde sitting somewhere. Why don't we just sample a random index between 1 and the size of witness, and I compare W and that witness? Okay? So sample I from 1 and whatever is the length of the witness, and check that Wi, so that's one query to W, equals a C tilde at the location or maybe C sub location I. When I say location I just mean, whatever is the index that you should be looking at if you expect to see Wi at that location, okay? All right. So let's try to analyze this. So this is the current candidate construction. Is it clear? All right. All right, for completeness, kind of if xw is in R, then we have to choose the proof pi, which equals what? Right, so to satisfy completeness, we need to say that, okay, we have a valid instance witness pair. We have to exhibit a proof that will make the verifier accept always. So we should make sure that the proof that we pick is which one? Can I pick any valid proof for the PCP verifier? I should pick which valid proof? The one that encodes W, right? So I could make the PCP verifier accept with any valid witness, right? But because I'm running a consistency check, I should pick the one that encodes specifically W, okay? So we can say encoding of W, and here aux prepared for W, okay? And remember, here I'm at a layer of abstraction. When I write this, I really mean, go back to a concrete construction and figure out what's going on, right? So this will make, so this makes the PCPP accept with probability 1. Okay, so that's good. All right, soundness. So let's see what soundness says. Soundness says that we're going to fix X. We don't know. It's maybe in the language, maybe outside the language. We don't know. Okay? We're also going to fix some W such that all we know is that it has distance from all valid witnesses for X at least delta. Okay? We're also going to fix a particular proof that is given to us. It's going to look like C tilde and aux tilde. Okay? Because that's, those are the kind of proofs we consider. All right, so we have two cases. There are two cases here to analysis. So one case is that, so what's the boring case, or the easy one to analyze? But we don't know, right? So we are in analysis. So first, we could do that, but we wouldn't learn too much. I think we want to sort of look at what happens. Okay, so I'm running the PCPP verifier. Okay, and let's focus for a moment on the first line. Look, either this guy accepts with high probability or not, right? Because that kind of, remember that we learn something only when it does, right? So the first case, the boring one, is to say V PCP given C tilde and pi tilde, an X does not accept with high probability. Okay? So this is the boring case, then we're done, right? Now, you may wonder, why is it not accepting with high probability? Well, one explanation, either X actually is not in L. That would be one explanation. But another explanation is that X is in L, so, or X is in L, and the proof pi tilde is stupid. Right? It could be, right? I don't know. So, if this guy, not pi tilde, sorry, this should have been aux tilde. And together it's all pi tilde. We don't know, right? All we know is that the verifier does not accept with high probability, and that's enough for us to kind of be done with this case. I'm just telling you, when that happens, you learn either that X is not in L, or X is in L, and pi tilde is just a bad proof. Okay? Remember that in this case, in the soundness case for PCPs of proximity, this is okay. Could be that X is in L, right? So the second case is that VPCP does accept with high probability. Okay? Now we learn something, right? We can apply this statement. We learn that the distance from C tilde to some valid witness is small. Right? Because it accepts the high probability. So, but remember, we're in the soundness case. So in this case, we have two tests. One is passing with high probability. Overall, we need to reject with high probability. So we must argue that the consistency check will fail with high probability. Right? So we now must argue that consistency test does not accept with high probability, right? This is our last resort. There's no other tests, Okay? And remember, in the soundness case, we have to reject with probability at most. We have to accept the probability at most s. So, and what's the argument here? So, well, you could say W is by definition delta far from Rx. Right? We know that, that's an assumption. Here it is. And then we can also say, well, C tilde is, say, delta prime close, where delta prime, say, small I define it to be delta prime here for a moment, is delta prime close to encoding of W with W tilde in Rx, right? And therefore, W is delta minus delta prime far from Rx. Sorry, far from C tilde. Therefore, the probability that consistency accepts is at most 1 minus delta prime. Okay, what am I trying to say here? Okay, wait, there's a bug somewhere here. Okay, so we'll see how it's uncovered. But let's try to understand intuition. I know that W, by definition, is far from all valid witnesses. I have a concrete guy, C tilde, which is close to some valid witness, or rather the encoding of some valid witness. And remember that the encoding is systematic, and we're checking C tilde on the systematic part against the witness. So now, because there is some noise on C tilde, I can't expect to really experience the full delta. Maybe C tilde is already moving in the direction of W, right? So I'll get a discount in delta prime. But the rest I'll catch. Okay? I claim this is a problem. Okay, this is basically what we wanted to say, but it's not technically true. Yeah?
If C tilde is close to an encoding, it might still be that all the errors are on the systematic location, and therefore the closeness doesn't give you any guarantees about those locations.
That's excellent. So we are applying these notions of fractional distance over different domains. Okay? Now the domain of W, you can think about it as a subset, okay, of the domain of the encoding. And the errors could be anywhere, right? You could have, for example, let's look at an encoding where it's, I don't know, 100 times bigger than whatever it encodes. And I'm telling you, look, C tilde is 10% close, to the encoding of a valid witness. But maybe these 10% errors are all piling up on the systematic part precisely to make it look like W. I'll never catch it, right? So that's a problem, okay? Because somehow my notion of percentage errors are kind of over wrong domains, and they could kind of conspire to be over domain that I care about, okay? So maybe let me say that one more time, because it's a subtle problem, and I'll make it even more explicit. Where do I want to go? I'm going to go here. The problem is, so the way I'm going to explain the problem is that instead of talking of fractional distances, I will talk about absolute distances. Okay, so I will make it clear. So we know that W differs. My D now is getting Greek. W differs in at least delta n locations from anything in Rx, right? That's what it means to be delta far. I need to change at least delta n locations to obtain anything in Rx. Let me just write it bigger. From anything in Rx. Good, all right. Then C tilde differs in at most delta, let's say capital N, locations from enc of W tilde for some W tilde in Rx, right? So all we can conclude here is that the distance between W and C tilde restricted to the systematic domain, actually I should have been more precise here. When I say W is delta minus delta prime far, from C, from C tilde, I meant C tilde restricted to the locations that I look, right? Because that's. So all I can conclude from these things is that this distance is at least delta n minus delta capital N divided by n, right? That's all I can really conclude. And if n, so there's a prime here, and if n is large enough, then this would be like a negative quantity and I conclude nothing, right? So like reasoning in absolute distances kind of clarifies what the issue was, okay? We were looking at different size domains. Sorry? So here I'm saying that n is the sort of size of W and capital N is the size of an encoding of W. And we expect generally n to be, big N to be much bigger than small n. For example, for Hadamard, it actually is exponential in size. And for polynomial PCPs, we polynomial size, right? So it might be like n to the 8 compared to n, right? Okay, so that's a problem, which is, all we can, and we cannot say much, right? So we don't know if this is greater or equal to what, 20, really. You can say it's maybe at least 0, but that's not very helpful. So the solution, so does anybody have any suggested solutions? Yeah?
Sorry, can you go over why it's a problem that you have this delta away that's greater than rho n?
So, okay, so you're asking from here to here, because once we're here, n can be much larger than n, and this would be, I can only conclude that it's at least 0, it doesn't help me. So we need to kind of, presumably you're asking about this part, right? I'm saying C tilde is defined over a domain of size capital N, right? And I know that C tilde is delta prime close to the encoding of something that is in W tilde. What I'm interested in is what happens when I look at C tilde restricted to the kind of message part and compare it to W. But these can be many, many errors, right? Because the domain is large, the fact that you're close in, say, 1% to a domain that is 1,000 times bigger doesn't mean much, because those are many, many errors. And all of those errors, they could, in principle, fall on the systematic part to make C tilde restricted to lock equal to W, okay? So that's a problem. Did I answer your question? Okay. What do we do about this? Yeah?
So we could compare an encoding of W to the encoding instead, and then if the code has a good distance, then you only need to check a small number of bits.
Sure, but that's cheating, right? Because that means that we have to change the definition, right? We only have W, right? So I have to be able to deal with kind of a raw W, like I don't have it encoded. And that would work, actually. And by the way, just for historical notes, the first paper that studied PCPs actually considered a setting where kind of your W was given to you encoded. Okay, this is something that they called holographic proofs. Okay, and yeah, in case you actually do go back and read some of these older papers, they were actually constructing implicitly PCPs of proximity under the promise that W is encoded. But we don't have such a promise, so we have to do something else. Yeah?
Shouldn't we be able to query non-systematic parts and learn about the systematic domain
Sure, but that has a name. Yeah, that's exactly. So we want to leverage the entire code word to some extent, but we've done that already before. So what did we do when we cared about a specific location of an encoding? We had this issue before. Yeah, we're getting. Let's proceed in a non-Zeno fashion so we can get there soon. Yeah, no, we're all going in the right direction. Yes. Yeah, we use the rest. We use randomization. What is this thing called? Or yeah, self-correction, right? So we want to self-correct the location, right? So we know we're interested in the location I, right? That's the location we care about. But maybe that particular location is noisy. Whatever, we'll just self-correct it, right? We'll just ask 10 other locations, and we'll infer from those 10 other locations what the correct value is for this one. Anyways, we know we're close, right? And for both of the codes that we've discussed, we have self-correction procedures. For this one, whenever you care about a particular location, you split it in two. You get back the answers, you add them back together. And provided that you were close, this has a high probability of success. We didn't talk about, but one can believe that for logic extensions, the same is true. Okay? How do you self-correct a logic extension? So we have a word that is written, and we know that the entire thing is close to the logic extension. So it's close to something that kind of extends whatever is here in the hypercube, right? And we're interested in a particular place here, but maybe there's an error here. Maybe there's an error. Okay? What do we do? Yeah? Yeah. And in particular, so there are many ways one can do it. A very straightforward way to do it is I pick a random line through the point. I read everything on that line, okay? And because I am close, to begin with, this line cannot on average have many errors, and it has a low degree, right? Because if the entire thing has degree D, a random line will have degree D, right? So provided that I don't have too many errors, when I correct this line, I will get the correct answer here, okay? So we're not going through this because we didn't use it before, and I think it's enough to have the mental image of self-correction for the linear functions. You can pass a random line. You can also find a random curve if you want, but it didn't really help, okay? All right, we can self-correct any of these things. So now we can go back and we can revise. So we're going to have a revision of our PCP of proximity. Revision. Okay. Where now, yes, we still pick a random I, but now we're going to run self-correct on the oracle C tilde, and we're going to pass in, say, please self-correct for me I don't know what layer of abstraction we want to write this, location I, okay? I'm interested in what is the value of the unique code word that is closest to C tilde, okay? And then you just query a few other locations, figure it out, you decode, and you compare that, okay? So we're not doing this instead, okay? So, so now the soundness analysis, okay, so the solution is self-correct. Use self-correction. By the way, we actually don't quite need the full power of self-correction. We only need something slightly weaker. Self-correction says that we can correct any location of the code word, whereas all we really care about is recover locations of the message. You see the difference? So this is the difference between what encoding theory is like locally correctable and locally decodable codes. Okay, correctable means that you can correct any location of the code word, and decodable means that all you're really asking is to recover positions of the message. which for systematic codes happens to be also part of the code word. So yeah, so here I'll just say in fact, local decoding would suffice. But for the both codes that we're looking, they actually have this stronger property. You can actually recover anything of the code word. Okay. And the analysis, for completeness doesn't change. For soundness, the first part here doesn't change. And let's make sure that we understand how to do soundness in the second case. Okay. So the main point is that for every I in W, the self-corrector at a location, say J, will equal encoding of W tilde at J, right? With high probability. Right? So whatever, okay, this is a J. For every, let me just, no, I want to write it differently. For every I in W, self-correct at location I will equal Wi tilde with high probability, right? The self-correct, we run the self-corrector on any index of interest, okay? The self-corrector is a probabilistic procedure. It will make a bunch of queries and say, please decode location I. With high probability, it will return the correct symbol of the unique code word closest to C tilde. Because we're at location I, what we will find is actually the ith location of W tilde, the message encoded, okay? So with high probability, let's call it with probability 1 minus epsilon. 1 minus epsilon. Okay? Then, in this case, the probability that the consistency test equals 1 is at most what? So before we were saying that probability is at most 1 minus delta prime. And now we want to say that it is at most what? Just to make sure that this works. So presumably, who will participate in this expression? Delta, right? Because delta matters, right? In particular, if delta is 0, what are we expecting, right? So W could be, say, one of the valid witnesses. In particular, could be the encoded code word. So delta should participate. Also, epsilon should participate, right? Because whenever the self-corrector screws up, we don't have any guarantees. So what should I write here?
So 1 minus epsilon times delta?
1 minus...
self-correction passes and...
why not something like this? I think that seems... I'm not sure about... The other one sounds... This is better. Right? No, the other one is... I don't think you can achieve it because you're making epsilon times delta is even smaller. This is better, I think. What is this saying? This is saying that I will... I'm running one test, right? With probability epsilon, that test just, is failing not because the test is not working, just because my self-correct answered garbage, right? But otherwise, if it doesn't answer garbage, I will experience the delta distance, right? Okay, that's good. So what do we learn? Now, basically, we don't really actually have a construction. We have a template construction, and we can instantiate in 2 regimes. This and that, right? So let's maybe write down in those 2 regimes what we've learned. We actually have this entire thing. We can literally apply it as a template, and it will give us 2 PCPPs in 2 different regimes. So we'll write them here, sort of a conclusion. We have proved that, and now we'd be tempted to write NP is contained in PCPP blah blah blah. I won't do that. I'll write actually something else, and we'll discuss why I'm not writing that. Okay. Well, what I will write is that a particular language, quadratic equations, which we've seen before, is contained in PCPP. Let's see first the exponential size regime. We have 1, 1/2, and then basically all of this stuff that we're doing, you can think about it that we can achieve constant proximity parameter, unspecified, so it doesn't matter, just some constant. And then poly n and O of 1. Okay, so this is basically saying that the exponential size PCP construction that we've seen can be augmented to be a PCP of proximity for the language that we were considering. And the other one, remember it was for the same language in the end that we looked at, was still quadratic equations, has a PCPP, again with perfect completeness, constant soundness, in particular soundness half, and constant proximity parameter. But now we have log n randomness and polylog n query complexity. Okay, so I claim that if you take this template and apply to our constructions, this is what comes out. Okay, and now we need to think about why didn't I not write for NP in general? Okay, and see what we can do about it. By the way, why are we learning both of these? We only had, I said that the outer PCP has to be robust, the inner PCP has to be proof of proximity. Why do we care about 2 proofs of proximity? Well, because actually we'll need proof of composition twice in a row. And one PCP will actually act both as an outer and as an inner PCP. So actually we will actually need both results. So that's fine. So now we want to somehow understand just how general is this result? Like, can we say something for all of NP? And if not, why not? Because, when we get to proof composition, we don't want to haggle about the specific language necessarily, right? That might be not convenient. So I claim that in a black box way, it is not the case that I can just take this one and deduce for NP. Why is that? So typically the way that you deduce something for all of NP is to say, well, I construct a proof system for a particular language, take the language that you started from, apply a reduction, right? And then run whatever proof system you had after you applied reduction. But now we have a problem. What's the problem?
Like something could be like accepting and something could be rejecting. And there could be like a very small difference between them. Like the distance doesn't really well.
Yeah, but can we be more precise? The distance over what?
Is it because of the relation? You have to define it as relation.
Well, I can have reductions between relations, but what do these reductions between relations do? They transform instances, but also transform what? Witnesses, right? Witnesses themselves change, right? When you have a reduction from one relation to another, it says, oh, you have some x, it goes to x prime. And then the completeness case says you have w, it goes to w prime, right? Where is w? It's gone, right? But the original w is the one we had to talk about, right? So yeah, sure, you can reduce to quadratic equations and you can talk about the new witness, but you can't talk about the original witness, which is what we wanted. So that's why actually we cannot, in general, talk about general NP reductions. There are a subclass of reductions that are called, guess what, systematic reductions, which basically say that, yeah, your witness changes, but if you look hard inside the witness, the new witness, you will find somewhere the old one, okay? And if you think about standard NP reductions, that's anyways what happens, okay? Somehow, when you do an NP reduction, you're not like literally changing the witness, you're augmenting it with other stuff, right? Not always, but many times. So kind of to extend to other relations, we should, at the very least, I say the very least because it's a necessary condition. It's not going to be sufficient for when I mention in a moment. At the very least, restrict our attention to systematic reductions. Okay, these reductions are the ones that send x to x prime, and the corresponding w goes to w prime, which equals w and stuff. Okay, so at least syntactically you can talk about w being already there, but this is not enough. Why?
Can all the errors still be on w and not the augmented stuff?
Right. So maybe my reduction augments the weakness by a lot. And now, kind of, if you think about it from the perspective of quadratic equations, we have a proof system that reasons about the witness for quadratic equations. And maybe this witness is 100 times bigger than the original witness I start from, and now my distance on the original one means nothing about the distance for the new one. Okay, so we're gonna have a problem. So at the very least, we need to consider systematic reductions. And then the second fix really is kind of inelegant, but it can be done, which is I actually need to change the verifier. How should I change the verifier to take into account that the witness has changed? Yeah.
Can you do the consistency check on just the systematic part?
Yeah.
And all the rest
exactly. So I just kind of redefine my notion of systematic to be the first one. Okay? I can apply a chain of systematic reductions, or just one systematic reduction, and I redefine my verifier here to sample among the subdomain of the subdomain, right? The one that contains the original witness, okay? And now my distance, will actually mean something, okay? So the second thing is a sort of modify the consistency check so that it considers the domain of the original witness. Now, so this is a recipe for extending this into other languages. I don't want to try to state under what conditions one can write a class of languages. All I really want to take out of this for next week is a corollary that says that we can go and apply these ideas and extend this to a somewhat more workable language of CSAT, just circuit SAT, okay? And even for CSAT, we do have to have these ideas because in circuit, you have your witness is just the inputs. But when you reduce to quadratic equations, you extend the witness to all the inner wires, okay? And it will be just much, much more convenient to apply these theorems for a language such as CSAT rather than quadratic equations, okay? So the punchline of today is that we have constructed PCPs of proximity for a particular NP-complete language, CSAT, okay, in both regimes, the exponential size and polynomial size regime, okay? Okay, so just next time we'll talk about robust PCPs and also a couple of logistics. We're approaching proposal and eventually also final project. And so Nick, I think, is going to produce at some point a post where you can also sign up to talk to him, and you can also email me, but in particular also with him, because Nick is going to give you in-person comments from the lecture notes to complement the ones he put already in the tech, and also you can take that opportunity to also sort of talk about the project as well. So if you want to meet with me, that's also okay, but separately you do need to meet with me, Nick, to talk about your scribe notes, okay? do take that as an opportunity also, because yeah, Nick is happy to talk to you. All right, see you on Thursday.